composite shafts, right? What are composite shafts? A solid shaft is rigidly sleeved by another shaft of different material, right? So this is called as a composite shaft. Now, why do you need composite shafts? Is many a times uh, there are different reasons. Now, you may want to avoid corrosion of a steel shaft, so you can put a thin sleeve of brass shaft over that, which can even help in because brass shafts are having very good bearing properties. So it helps in bearing also that shaft. Right? For this reason, we do this, and sometimes the ends are also welded together. The composite shafts behave like a solid shaft, behaves like a single solid shaft. So the torque transmitted by the composite shaft is shared by both the shafts, and the angle of twist and length is same for both the shafts, right? So if you just see this, here also we have the angle of twist is same and the torque transmitted is sum. So it is like shafts in parallel. The composite shafts are like shafts in parallel. We can calculate the individual torque transmitted by equating the angle of twist for both the shafts, right? You have to calculate theta 1 and theta 2 and then equate them, because theta 1 is equal to theta 2, and from that you can calculate the torque that is transmitted. The next topic is strain energy due to torsion. This is a very small derivation, you will see this. Now I have the strain energy stored in any body is given by U is equal to tau square by 2c into V, where tau is shear stress, C is the modulus of rigidity, and V is the volume of the body. Now I'm considering a shaft, circular shaft, where the torsional shear stress is zero at the center and it is maximum at the surface. So the shear stress is varying from zero to maximum from the center of shaft to the surface of the shaft. Now in this shaft, I am considering a small element, circular element of thickness dx at a radius x from the center. Now the area of this circular element is 2 pi x into dx, and the shear stress developed at this section. Now you imagine this shaft is having some length of L, right? And this elemental volume will be dA into L. So I am using that in this. The shear stress developed at this section, we have derived this already. Tau x by x is equal to tau by r, or tau x is equal to tau into x by r, right? Now the strain energy stored in this element, now I know the shear stress, I know the volume, I can calculate this. It is tau square by 2c into V volume. So tau is tau x here, so tau x square by 2c into L into dA. L is the length of the shaft, dA is the area of the element. I'm just putting this value of tau x as tau into x by r whole square into L into, I'm putting dA as 2 pi x dx. And when you just rearrange, and what I've done is I've taken all the constants together here. So this 2 pi L comes out, tau square comes out here, and r square by r square is there, that also comes out here. So I have x square into x, so that becomes x cube into dx. Now the total strain energy of the shaft can be calculated by integrating this equation between the limits 0, that is the center of the shaft, to r, that is the outer surface of the shaft. So when you do that, it is integral of x cube dx. So we get x power 4 by 4, and the limits is 0 to r. Now when you substitute r in this, so you get pi l tau square r raised to 4 by 4 c r square. Now r square gets cancelled, so it is pi l tau square r square by 4c. Now L pi r square is nothing but pi r square is area of this circle into L is volume of the shaft. So tau square by 4c into volume of shaft. That is the equation for calculating the strain energy stored in the shaft. Now in the same lines, if you do the derivation for a circular hollow circular shaft, you get the strain energy stored in hollow circular shaft as tau square by 4c d square minus d square by d square into V, right, where V is the volume of the hollow shaft.